everyone, thank you so much for coming to this lesson. So today we're going to be going through Surds for AS and A-level maths. So this topic has it's got some referencing to indices, so make sure you look through that video as well, as it will be quite helpful. So the learning objective for this lesson is to be able to use and manipulate surds, including rationalizing the denominator. So in this lesson, I'm going to take you through 3 different rules that are really helpful for surds manipulation, and some examples on how you can use these, and also some practice questions. So as always, there's going to be timestamps in this description, so feel free to skip any parts or skip to any parts that it will be helpful to you. So let's get started. So firstly, what is a surd? So a surd is basically just a square root of number that cannot be simplified to a whole number. So for example, you could have root 2, and that's equal to like 2.14, like etc. And as you can see, root 2 is not a whole number. But then let's say you have a square root of 4, that's equal to 2, which is a whole number. So that means square root of 2 is a surd, but then square root of 4 is not a surd, because root 4 is just 2 is a whole number. So yeah, a surd is always a square root of number that cannot be simplified to a whole number. So just remember that. So you can also, if you remember the work we did in indices, you can also write surds in the form of an index number. So if you remember, if you have like 2 to the power of a half, for example, that's the same as just the square root of 2. So you could just write a surd by raising the power of that number to a half. So that's just an overview of what surds are. As I said before, we have 3 rules that are really useful when manipulating different expressions that involve surds. So the first rule we have is root of AB is equal to the root of A times the root of B. So another way to think about this is using indices. So let's say you had AB to the power of half. You can just like simplify that, and just because it's a multiplication or to the power of half, you can just do each one individually and multiply them together. So you could just do A to the power of half times B to the power of half, and as I said before, anything to the raised to the power of half, that's just the square root of that. So that's just equal to the square root of A times the square root of B. So yeah, so let's show an example of how you use this. So let's say you had a surd root 12 and you wanted to simplify that. So you could simplify this by breaking. So first you need to think about what are the different factors of 6. How can I split this up? So one way could be 6 times 2 is 12. So you could write this as 6 times 2. Now, neither 6 or 2 can be, both of them are surds, so that's not really that helpful. So you could simplify this way, but that's not really going to take you that far. So let's think of another way we could simplify, break down 12 into 2 of its factors. So another way could be root 12 could be equal to root 4 times root 3. And then as we know, root 4 is just the same as 2, so that's just equal to 2 root 3. So you can simplify, using this first rule, you can simplify root 12 as just 2 root 3. So the second rule you have is the square root of A over B is equal to the square root of A over the square root of B. So similarly, you can think of this using indices. So you could say A over B to the power of half. If you do each of them individually, that's just A to the half over B to the half, which is just root A over root B. So it's really similar to the multiplication rule. So one way, so like an example of how you could apply this. So let's say you had this third root 3 over 16, and you wanted to simplify that. So using this rule, you can just simplify that as being root 3 over root 16. And you know that root 16 is the same as 4, so that's just equal to root 3 over 4. So that's just, using this rule, you could just simplify this expression really easily to root 3 over 4, which would be much easier to use in like more complicated questions. The last rule you have is just a equals root a squared. So this is just saying if you have like a third and you square that, that's just equal to the number that's like in the square root. So let's say you have for example you have root 2 squared, that's just equal to 2. So you could also think this in terms of indices. So if you rewrite root 2 in terms of indices, you'd have that's 2 to the power of half. And if you square root that, if you remember going back to the index powers, what you do is you just do half times 2. So that's just equal to 2 to the power of 1, which is just 2. So an example of how you'd use this rule is when you're multiplying out expressions and multiplying out brackets. It will come extremely useful in that. So let's say, for example, we had 2 root 5 plus 3 root 6, and we wanted to square that. So when you multiply out the brackets, if you remember, you just do term by term. So let's say, the first term in that would just be 2 root 5 squared, and then you would have 2 times 2 root 5 times 3 root 6, and the last expression would just be 9 root 6 squared. If you've forgotten how to like multiply out brackets, just review that lesson, and you can go back to that and you can come back to this after once you review that. So this would just be, if you take each term in the bracket individually, so you start off at 2 squared, that's just 4, and then root 5 squared, using this rule we've just gone through, that would just be equal to 5, so it's 4 times 5, and plus you times all the whole numbers first, you do 2 times 2 times 3, so that's just 12. And then you do root 5 times root 6, and then using this first rule is root 5 times root 6, that's just equal to the root of 5 times 6, so it's just the root of 5 times 6. And then you plus, sorry, this should be 3. And then a step ahead of myself. So then you just do, so 3 root squared, so you do 3 squared, so that's just 9. And then you do root 6 squared, so that's just times 6. And then this would all simplify to 20 plus 12 root 30 plus 54, which is just equal to 74 plus 12 root 30. So the next part of the lesson is going to be about how to rationalize the denominator. So rationalizing the denominator is just trying to make, if you have a third at the bottom, it's just trying to make sure that trying to turn that third into a whole number. So for example, let's say you have 1 over 1 plus root 2. So to rationalize that, you want to try and get rid of the root 2 at this bottom, and you want to try and make that a whole number. So to do this, you need to try and multiply the top and the bottom by the same expression in order to get rid of the third. So one way you could do this is by multiplying each bit by root 2. And the way why this works is, if you remember, that is like, so the way this works, this one is like, if you remember, if you have like A plus B and you times that by A minus B, that's just the same as A squared minus B squared. So it's just like the difference of two squares. So that's why if you ever have an expression that's just like one, like if anything is in like the form of this, either this one or this one, in order to rationalize the denominator, you just times top and bottom by the other one. So in this way, in this one, because it was 1 plus root 2, we just times both top and bottom of the fraction by 1 minus root 2. So then you can simplify this further. So the top would just be 1 minus root 2, and then the bottom would just be 1, and then this would cancel out, minus 2 plus root 2, that would just cancel out, and then you just have minus root 2 squared, and then going back to this rule here, that's just 2, 1 minus 2. So then the whole expression is 1 minus root 2 over minus 1, which you can also write as root 2 minus 1. Another example, let's say you have 9 root 3. To rationalize this, you just want to turn this bottom, the new denominator, into a whole number. So you can go refer back to this rule. You know, if you square root 3, you'll just get 3. So you just multiply the top and bottom by root 3, and then you just get 9 root 3 over 3, which you can simplify further. You could just cancel out the 3, so you'll just get 3 root 3. So now we're going to move on to some practice questions to see if you've understood what we've discussed in the lesson. So here's the first question. You need to simplify 7 plus root 5 divided by root 5 minus 1. So I recommend you just pause the video, try this out, and then come back and we can go through it. So, so this question is saying to simplify it, and you should notice immediately that this should be a rationalizing the denominator one, because it's a fraction, and then in the denominator you have a surd number 5, so you want to try rationalize it. So to do this, if you remember that if you have something in the form like this is in the form a minus b, with root 5 being a and b being minus 1, you just have to times top and bottom by a plus b. So in this example, we're going to times both top, bottom and top by root 5 plus 1. So now we need to use some of the other rules that we went through. So if we multiply out the brackets, you have 7 times 5, so just 7 root 5. And then you have 7 times 1, so plus 7. And then you have root 5 times root 5, so that's root 5 squared. So using the rest rule, that's just equal to 5 plus root 5. And then that's all over root 5 squared again, which is just 5. And then root 5 minus root 5 cancel out each other, and then minus 1. So that's just equal to, if you have 7 root 5 plus root 5, that's just 8 lots of root 5 plus 7 plus 5 is 12 over 4. And then you can simplify this further by cancelling out the 4, and then yeah, that, and then you'll just have 2 root 5 plus 3. So yeah, that's basically just all there is to Surds. So yeah, I hope you found this lesson really useful, and you now know the different rules that we use to manipulate Surds, and you've learned how to rationalize the denominator. So yeah, just make sure you remember all those rules of Surds we went through, and just memorize them, and do some practice questions to make sure you fully understand the topic. But yeah, thank you.